Today, ladies and gentlemen, we're going to start Chapter 9, even though I'm not with you. That's okay, you don't need me. We'll be doing 9.1, Basic Combinatorics. Now, today, ladies and gentlemen, essentially what I'm teaching you to do is I'm teaching you how to count. Now, obviously, this is not the 1, 2, 3, 4, 5, 6, 7 counting. It's counting possibilities of things. If I have, say 20 students in a room and 4 of them get to have A's, how many different groups of 4 can I make out of the 20? That's the kind of thing we're going to be doing today. We will talk about the multiplication principle of counting, also called the fundamental theorem of counting or fundamental principle of counting. Permutations, combinations, you've probably seen a lot of these terms before if you have done prob and stats or maybe some Algebra 2 classes also. So we'll start with this problem. Let me get this box out of the way. 8 pieces of paper are numbered 1 from 8. They're placed in a box. One piece of paper is drawn from the box. Its number is written down. The piece of paper is then replaced in the box, and a second piece of paper is drawn from the box. And his number is then written down, and then finally we go on from there. So the two numbers are added together. How many different ways can the sum of the added numbers be equal to 12? So how do we begin this problem? Well, first of all, I consider all the possible ways that the paper could turn out. Now let me go ahead and tell you as you're watching this, you may want to pause the video at times. If you want to try and work the problems out on your own, just have the substitute pause the video. Not a big deal. If you want to just go on through, that's fine. I usually don't leave much time for you to work it yourself, so if you do want the time, you'll have to pause the videos. So what are my possibilities? Well, one possibility is I could draw a 1 out first, and then when I put it back, I could get 1 again. Or I could get a 1 and then a 2, and a 1 and a 3, and all the way down to 1 and 8. Another possibility is I could start with a 2 first, and then put it back and draw a 1, or a 2 and a 2, and then all the way down through 8, and then so on. So we see here all the different ways that the slips of papers can be drawn. But now how many of these add up to 12? Well, 4 8 adds up to 12. 5 and 7, 6 and 6, 7 and 5, 8 and 4. So how many different ways can we add up to 12? Oh, sorry about that. 1, 2, 3, 4, 5. Looks like 5 total. Now what if the problem has changed ever so slightly, but this time when the two papers are drawn, they're drawn at the same time. In other words, you pick 1 out and then you don't put it back, so there are only 7 possibilities the next time, if you will. So now how many times can we get a 12? Well, again, we start with this possibility. But because of how the problem has changed, you'll notice that some of these are no longer possibilities. For instance, I could not get, I could not get a 1 and a 1, or a 2 and a 2, or a 3 and a 3, or a 4 and 4. Why not? Well, the way I would have gotten, say, the 4 and the 4 before was to draw 4, put it back, and then draw the same slip of paper. Remember, I'm not putting it back this time. So the doubles are impossible on this problem. So if I look at the ways to get a 12 right there, and I take out all the doubles right there, you see what's left over. 1, 2, 3, 4 ways to get a 12. Alright, next problem. How many 3-letter codes can be formed using the letters A, B, C, and D? And again, if you want to try this one on your own, go ahead and pause the video. Well, there's several ways to approach this problem. Again, just like I did on the last problem, I can start out by listing things in a very orderly manner. So, for instance, I could start out with A first. If I start with A first, that could be followed by BC, or BD, or CB, or CD, or DB, or DC. Or I could start out with a B first, or C first, or D first. But you got to be careful this way, ladies and gentlemen. It's very complicated. Well, I wouldn't say it's complicated, but it's very easy to make a mistake. But if we do it this way and we count, you see we have 6 columns of 4. 6 times 4 is 24. Now there's another way to do this problem. Again, for you artistic visual people, it's what we call a tree diagram. Now I'm going to have to adjust the screen just a little bit for you to see the tree diagram. I'll move the screen down, and now hopefully you can see everything. But you see we start out with a single point up top, and we go to our first possibilities, which could be A, B, C, or D. Now for each A, we could have B, C, or D. For each B, we could have A, C, or D, and then so on across. Then for every AB possibility, you could have C or D. So, for instance, you could have the ABC, there's one. You could have ABD, there's one. You could have ACB or ACD, there's two more, and then you do that all the way across. Now, this really is no different than what we did on the previous slide, where we were just listing them out in an orderly fashion. This just gives you a visual representation of that for those of you maybe that have trouble seeing it in your mind. Now, the fundamental counting principle, also called, I think it is something about the multiplication principle of counting. They're the same thing. What is the fundamental counting principle? It says if you have two events, E1 and E2, and the first event can occur a certain number of ways, and the second event can occur a certain number of ways, and you're going to pick both of those events, then the number of total ways that you can have it is M1 times M2, or the number of ways the first event can occur times the number of ways the second event can occur. Now, if you want to think about this, consider the fact if you have, for instance, maybe 3 shirts that you want to wear and 4 pairs of pants that you can wear with it. Well, how many total outfits do you have? 3 shirts and 4 pants. For every one of the 3 shirts, you have 4 possibilities of pants. 3 times 4, and you would have 12 possibilities. Now, some of you ladies may tell me that that's not a possibility because not everything may match, but mathematically speaking, that is the correct conclusion. Now, let's use this counting, multiplication, fundamental counting principle, whatever you want to call it, to work this problem. Telephone numbers in the U.S. have 10 digits, the first 3 being area code, then the next 3, and then the next 7. How many different telephone numbers are possible within each area code? So we're going to ignore the first 3, the 865, if you will, for our area. How many different possibilities do we have? Now, it is worth noting that no telephone number can start with a 0 or with a 1. Obviously, because 0 starts out for the operator and 1 starts out for long distance. So how are we going to do this? Well, if I consider 7 possibilities, the first of the 7 numbers can have 8 possibilities. It can have a 2, 3, 4, 5, 6, 7, 8, 9. That's 8 possibilities. Again, it's not 10 because you could not have the 0 or the 1. But now every other number past that can have whatever it wants. So we could have 10 for the next one, 10 for the next one, and then the next, and the next, and the next, and the next. And if you take all those numbers and multiply together, you see that within each and every area code, you do have 8 million possibilities. Now, I will also say that that's not entirely correct, simply because there is one possibility that we're leaving out. Along with no 0 or 1 right here, you also cannot start out a phone number 911. So you figure out how many possibilities that would take away and see if you can do that on your own. Alright, what about this one? How many letter pairs, how many different pairs of letters from the English alphabet are possible? Well, again, I pick one letter with a certain number of possibilities, and I pick another letter with a certain number of possibilities, and I put them together. So, how many letters are there in the alphabet? Well, I've got 26, and I've got another 26. Now, notice that it doesn't say anything about doubles are not allowed. If it had, it would have changed it. You think about what kind of a change that might make. But all it says is letter pair. So, 26 letters for the first, 26 letters for the second. Multiply them together. Again, ladies and gentlemen, if we're moving too quickly, just ask the substitute to pause and let you catch up. And you are welcome to back up the video at any point in time also if you need to. 26 times 26, 676 possibilities. Alright, another one. If a license plate has 4 letters followed by 3 numerical digits, find the number of different license plates that are possible if no restrictions to letters or digits can be used. So we have 4 letters and we have 3 digits. Well, if we consider 4 letters, that's 26 times 26 times 26 times 26. Again, notice it said no restriction, so repeats are okay. And then we've got 3 numbers. There are 10 digits, so 10, 10, and 10. Multiply all those together, 456,976,000 possible license plates. Now, this brings us to another vocabulary term, permutation. An important application of this fundamental counting principle is in determining the number of ways that n elements can be arranged in order. You have 20 books to put on a shelf. How many different ways can I arrange them? That kind of thing. The ordering of n elements is called a permutation of the elements. So whenever you see the word permutation, you need to think about putting things into a certain order. Now, how many possibilities do I have? Well, to figure out the number of permutations, we do a factorial. So again, going back to the previous example I'd mentioned, if you had 20 books to put on a shelf, how many ways could you arrange them? Well, you would have 20 books for the first spot, then you use one, then you'd have 19 for the next spot, then 18, then 17, 16, and on down. You see the digits are decreasing all the way down to 1, and multiply those together. That's n factorial. Let me go back. Sorry, I didn't mean to advance the slide there. N factorial. That's how you would figure out how many different orders or ways you could order the books. So, let's consider this one. How many different permutations are possible for the letters A, B, C, D, E, and F? Well, on the first letter possible, we would have 1, 2, 3, 4, 5, 6 possibilities. But then I use one of those letters, so the next letter would only have 5 possibilities, and then after that I've used 2, so then there's only 4, then 3, then 2, then 1. So it looks like this. All letters are available here. Here I've used 1, now I've used 2, and 3, and so on. And of course you should recognize this as 6 factorial, which is 720. Distinguishable permutations. Count the number of different 8-letter words that can be formed using the letters in the word computer. So how many different ways can I arrange letters? Again, the letters don't have to make sense. They don't have to actually make a word. It's just how many ways can I arrange the letters. Well, again, it's important to note in the word computer there is no repetition of letters. When there is repetition of letters, it changes slightly. So I've got 8 possibilities for the first and 7, 6 all the way down. So 8 factorial, which is 40,320. Again, reminding you, pause the video as needed because I know I'm going through quickly. Alright, another one. 8 horses are running in a race. In how many different ways can these horses come in first, second, and third? Assume no ties. Now, ladies and gentlemen, I show you this problem because I want to point out to you that this is not a strict permutation problem. For the simple reason, I can't just do 8 factorial. Why can I not do 8 factorial? Well, there's only 3 different spots, first, second, third. Nor can I do 3 factorial because there are 8 horses. So how would I work this one out? Well, how many horses do I have for the first winning spot? I have 8. Now, assuming 1 horse wins, how many do I now have for the next spot? I have 7. And then, assuming those 2 horses, I have 6 possibilities for third place. And we have 336. This is still a permutation, but it's a different kind of permutation. We call this a permutation with only a certain number of objects taken at a time. You'll see that here in just a second. And here we go. First of all, back to the distinguishable permutations. Ladies and gentlemen, if you have a repetition of objects, so again, consider the word Tennessee, and I wanted to know how many ways that I could rearrange the letters of Tennessee. Well, Tennessee has how many letters? Figure that out. I think it's 9 letters if I'm counting there on my fingers correctly. Well, I could do 9 factorial, but the problem is I've got repeats of S's and E's and N's. So to eliminate the words that are basically the same, where maybe just 2 N's have switched places, I do this. N factorial represents the total number of letters in the word. N1 factorial is however many letters I have repeating of a given letter. So for instance, if there's 4 letters that repeat, say 4 E's in a word, I would do 4 factorial. If there's 3 S's, I would do 3 factorial, and so on and so on. And you'll see this used in another example here coming up. Now, this video is only allotted to me to be 15 minutes, so I'm going to have to pause the video right now, and there will be a second video following to finish up the lesson.